Thanks a lot, Macarena, and it's been wonderful being here. Enough time to think and wonderful lots of workshops and talks. It's great. Very appropriate mix. Okay, so I won't define these terms right away, but I should say that I have borrowed these two words from Neer. Yeah. Okay. Yeah. Okay, good. So let's see. So I said I'll mention some questions, and I think some questions are going to be ill-defined. But let me just put this as a motivation. The motivation is develop a Nielsen-Thurston classification for commensurators of G equal to pi 1s, yeah? Closed surface. And more generally, G hyperbolic. And what do I mean by Nielsen-Thurston classification? I mean basically classification of commensurators into elliptic, parabolic, hyperbolic. What's the analog? Yeah? So it's not clearly defined, but that's a kind of motivating question behind this talk. Okay, so what's a commensurator? So you have H contained in G. So let's say it's a subgroup of a group. It's a definition. Is commensurated. So is commensurated by the ambient group G if for all G belonging to the bigger group, the conjugate is of, so the intersection of the conjugate of H with H is of finite index in H. Okay. So, and yeah, so this is true for all elements of G. Okay, so what are the, I mean, of course, and we write, so this way, so also say that H is almost normal in G. Yeah. So this word is, yeah, almost means nothing really. Yes, but you can flip this around and, yeah, let's write it. Okay. Okay, so so this is the starting point, and let me just start with one prototypical example. Pardon me? Yes? Oh, I just said, I mean, it's the same thing as if H is commensurate. This is just another way of saying the same thing. Yeah. And this word almost is it really means not too much. Okay. All right. So what's the prototype? I mean, here's the motivation example. H is SL2Z, and G is SL2Z adjoined 1 by P. So this is the same thing as the group generated by H and this matrix inside SL2Q, inside SL2R. Okay, so this is one example, and it will turn out to be an example of an elliptic. I mean, so all elements of this bigger group will commensurate this because this particular diagonal matrix commensurates SL2Z. Yeah? and the commensurator is a group. Therefore, this happens. We'll say a little more about what is the dynamical classification. Yeah. This will turn out to be something that's elliptic. All right. But more general examples. So let's say L naught. L is so there are two themes that will interact a little bit during the course of this talk. One is basically the theory of totally disconnected locally compact groups, and the other is what we all love, finitely generated discrete groups. So here, and we'll say how to go between these two languages very soon. So let's say L is a locally compact, totally disconnected group. And I'll shorten this to the usual thing, TDLC. And L naught is a compact open subgroup. Then L naught is almost normal in here. Basically, because if you look at a conjugate of a compact open by any element of the ambient group, that's a compact open. So you look at the intersection, that's compact open. So compact in a compact is going to be, compact open in a compact open is going to be finite index. So this is a standard thing. And a little more, if G is just now an abstract subgroup of L, is dense in the topology of L, and H is equal to G intersect the compact open, then H is almost normal in G. So this passes to so this passes to dense subgroups. All right. And in a certain sense, that's what I'm going to say now, this example here, let's give this guy a name, example 2. So fact is that this example 2 is universal. I mean, essentially, what does that mean? In the following sense. So let's say you have H normal in G, then G acts on G mod H. Just think of G mod H not as a Schreier graph, but just as a discrete set. It's a collection of cosets. And via this action, so this is with discrete topology. This guy, just the collection of cosets. And equip G with, I'll write compact open. Topology, which means that basically two elements of G are closed if they agree on large finite sets. And let G double slash H, are there algebraic geometers in the audience? No, good. Yeah, I always, get into this. Yeah, so this has a different name. I mean, it's not the GIT quotient. So this is called the Schlichting completion. Oh boy, completion, which is completion of G with respect to this topology. And this guy, I'll just call it G mod mod H. This is a TDLC. And the closure of H in this is a compact open. Okay. So let's revisit this prototypical example there. Let's say H is equal to SL2Z and G is SL2 Z1 by P. This is the example that we started off with. Then, so example again. And this, the Schlichting completion is just SL2 QP, and H bar is equal to SL2 ZP. So the p-adic completion of Q and of SL2. Okay. And of course, G is dense in this guy. All right. So yeah, I mean, part of this talk is going to be kind of general nonsense in the sense that, yeah, this is in the sense that there are very general constructions that one can do and one can. Okay. So now suppose you have G is, okay, now let's write L. L is, suppose it's a compactly generated group. So is there, so basically what we'll go on from here to say is essentially that there is an analog of the Cayley graph here, yeah, in this setup of TDLC groups. So this is called the Cayley-Abels graph. So we have to find this. So suppose L is compactly generated and L naught is a compact open in L, so that L is generated by L naught and some finitely many elements. Yeah? Then there exists a graph with bounded valence G, such that G acts on, L acts on G transitively, and the stabilizers of vertices L, these are conjugates of L naught. And again, revisit this example. So for L equal to SL2 QP, L naught equal to SL2 ZP, the Cayley-Abels graph, this is the Bass-Set tree. It's exactly the Bass-Set tree for SL2 Z1 by P of this form where A is SL2Z, B is, I haven't given this guy a name. Let's call this matrix P. This is A conjugated by P, and C is the intersection of A and B. Okay? And this is exactly the same. So this is the Bass-Set tree for this finitely generated stuff that we all know. It's also the as set tree for SL2QP with vertex stabilizers SL2CP conjugates of those. So this is basically Serres-Bourcon trees, but it's, and the reason why I'm bringing these examples up, it's basically says that at least the underlying graph, the Cayley-Abels graph here, yeah, is the same whether you're looking at it in the TDLC setup or in the geometric group theory setup. Yeah. So, but I mean the graph is easier to extract from the TDLC group, and so we've done it this way. Okay. All right, fine, but here is one of the yeah. So again, this is again an ill-formed question, but how does the TDLC perspective interact with the discrete group perspective? I'll say a word about this. Basically, what's happening here is that the stabilizers of vertices in the TDLC, I mean, these are compact, totally disconnected groups. So you should think of these as basically profinite, some kind of profinite completions or completion with respect to some family of finite index subgroups of the stabilizer of the group. Yeah? What that means is that this whole beautiful geometric object SL2Z, which we know and love, has lost all its geometric structure and has now been compactified into something and then densely embedded there. And the Cayley graph structure, that's what I mean by the geometric structure, is essentially lost at first glance. Yeah? I'll say a little more about this and maybe a little later. Okay, fine. So one more thing is that you can think of the group, the compact open, as acting on the TDLC, so which means basically it acts on it and preserves the map down to the base, at least at the origin, yeah? Because it's a stabilizer of a vertex. And so it really fixes a vertex and acts essentially elliptically. I mean, it's with some fixed point, and it permeates all the edges around it. Okay, so which means it's, well, in some sense, it's a kind of a bundle over a graph where the fibers are compact objects. It's one way of thinking about it. That's not the way we as, geometric group theorists think. So is there a way of recovering a bundle structure over the Cayley-Abels graph in the discrete setup? That's what we'll go to now. So now suppose H is finitely generated. Yeah, both G and H are finitely generated, and assume that the generating set for G contains the generating set for H. So then the Cayley graph of G, this admits a map to the Cayley-Abels graph that we extracted from the TDLC perspective. And there are fibers. So the fibers over vertices are all isometric to gamma H. there's a little more. Further, if you have an edge in the Cayley-Abels graph, then there exists a map phi VW from gamma V, which I'm thinking of as the stabilizer of the vertex V, to gamma W, which is K epsilon quasi-isometry. This is uniform, independent of V and W. Yeah? So think of the prototypical, I mean, the classical cases where you have a normal subgroup, not almost, genuine normal subgroup of a bigger group, and everything is finitely generated. Then you take the finite generating set for the big group G, push it down to a generating set for the quotient, and then you have a genuine map from the big group to the quotient group, and fibers are all H and its conjugates, and the map is basically a map which takes H to a conjugate of H. Yeah? Since there are finitely many generators, each has some quasi-isometry constant, you take the maximum of all these guys. Yeah? And here in this almost stuff, all that's happening is that the quotient guy is not necessarily a Cayley graph of a quotient group, but it's just a space. It's a homogeneous space, it's acted upon by G. And the rest of the technology goes through. All right. So something which satisfies this kind of stuff, it's got a name. So it's got so gamma G has the structure of a metric bundle over the base G with fibers gamma H. All right. So now I think, yeah, we have all the general stuff. Oh, that's not so bad. Good. Okay. So we have all the general stuff that we needed to introduce for, yeah, so again, visiting the, so the classical example, SL2Z1 by P, your fibers are SL2Z, the base is your Bass set tree, and you go on. So that's a real example where it's not a normal subgroup. Okay, so once we are done with this, let's now define what hyperbolic guys are and what elliptic guys are. Okay, so let's definition once more, and this is yes.
That the uniformity with the neighbors, but I don't know that uniformity along paths.
So
it's not true that there is a uniform quasi-isometry between any two vertices.
No, that's not. Yeah, that's right. That's right. So you just need a uniform quasi-isometry between. I mean, so the map. So for instance, I mean, suppose you had the simplest case. You take a the simplest case means the way a place where this all comes from. So take a hyperbolic three manifold fibering over the circle. Yeah? So you have a surface group, which is a normal group, a normal subgroup, and the quotient is a Z. Yeah? So, and the monodromy is a pseudo-anisop, let's say if it's a phi. Yeah? So phi is a uniform quasi-isometry, but phi power n, as you change, it's not. Some things get contracted by some lambda power n. Yeah. So the same thing is true in the quotient setup. All right. So yeah. So the terminology that I'll be introducing right now is just for the purposes of this talk. Yeah. Don't hold me to account for this. Okay. So we'll say that yeah. H is almost normal in G. This is, so G strongly, this is just the setup, yeah? So it's G strongly, hyperbolically commensurates H if, okay, G is hyperbolic and H is hyperbolic. So let's put this hypothesis. So H is always going to be hyperbolic for us, and you put it in a bigger group, and you say that the commensuration is strongly hyperbolic if the ambient group itself is hyperbolic. Yeah? So what are we thinking of? We are thinking of G is in the abstract commensurator of H, and just think of the group generated by, so think that the group generated by H and G itself is your bigger group G, and the bigger group is hyperbolic. And can this happen? So what are restrictions on H and hopefully on G? And so the theorem is joint work with Near, Alex Margolis, and it basically says that if under this hypothesis H is virtually a free product of surface groups and a free group. Okay. So what's going on here? It's basically, so the classical case where H is actually normal in G. This is a consequence of the Ripsala theory. So basically what you do, you look at some element, little g of capital G, take large powers, so that's going to conjugate your H, and you pass to a scaling limit, your H becomes now an R-tree because H is hyperbolic. Because it's a hyperbolic automorphism, it stretches some directions, contracts some other directions. So you finally end up getting a free action of H on an R-tree. Yeah? It's a finitely generated group. And then you put the Rips machine and you extract that information. Yeah? So here, because it's a commensuration, you can't quite do the rescaling. However, the theorem still goes through. It's the same classification. Okay, so this is what one can say about H. And the question that had posed was, well, can you say something about G? Unfortunately, I don't have an answer. Okay, but one can say a little bit about, what about G? That's the Cayley-Abels graph. Yes?
Other examples.
Yes. I'll come to that. And thank you very much for that question. I was about to miss that in my head. Yes. So there are examples. All right. So we can't quite say what the restrictions are on G, but it's really, I mean, what are restrictions on the quotient space? So restrictions on the Cayley-Abels graph. So first, yes. Yes. No, you get exactly the same statement. Yes. So what about restrictions on G? And so first, First, G is hyperbolic. Okay. Again, in the case where this was a normal subgroup, this is a theorem of Moshe from the mid-90s. Yeah? So basically, if you have a hyperbolic subgroup of hyperbolic normal subgroup for hyperbolic group, the quotient group is hyperbolic. So here you get that the space is hyperbolic, and the proof is essentially the same, except that, yeah, you have to replace the group theory by this metric bundle terminology, and essentially the rest of it goes through. But here's the point. Let's say, so I am yet to answer Henry's question. So let me paraphrase your question. Are there real examples? Yeah. And yes, I've said that, yeah, given a very doctrinaire answer, that there are examples. But let's take that for granted for now, and say that if H almost normal in G is a genuine example, what that means is that it's not normal up to passing through finite index subgroups, et cetera, then boundary G cannot be equal to the circle, the sphere, or the three-sphere. So that's a little mystifying. But so what's really going on? And this is the one place I know where the TDLC perspective and the geometric perspective actually work with each other. So what happens is that, look, if you pass to this TDLC perspective, H now becomes a compact totally disconnected group. Yeah? And if it's so that guy is fixing a point, and it's rotating if you think of this Cayley-Abels graph being rotated around that vertex. I mean, it acts on it by cellular isometries. So and G is hyperbolic. So it acts by homeomorphisms on the boundary of G. Yeah? But you have a totally disconnected group, and I'm saying that it's a genuine example, so up to finite index, let's say, or it has a totally disconnected subgroup, which is indiscrete, which acts faithfully on the boundary. Yeah? So if the boundary is a manifold, that's something that one expects not to hold. Yeah? So this part, what's this? These are the only cases where the Hilbert-Smith conjecture is known. That's all it means. Okay. So yeah, I mean, so basically you can't have the closure of a Z inside a ZP or an abelian, a cyclic, topologically cyclic, totally disconnected group, locally compact. These are manifolds that you know it can't act on. So yeah, one expects that. Oh yeah, of course. Yeah, of course not. I mean, this is a cheat, really. It's basically saying you have this totally disconnected group, it acts by homeomorphisms. You take this big theorem of John Pardon and Montgomery Zepin and all these people from the shelf, and just say, okay, apply it, and you have this stuff for free. So what's yes? Boundary of? Oops. No, the Cayley-Abels group, the quotient group. So this is to be contrasted with, well, so this recent result, or well, not that recent, it's a little more than a year now. Kent and Leininger proved the existence of purely pseudo-Anosov surface subgroups sitting inside the mapping class group. Okay? What that gives you is basically an exact sequence where the normal subgroup is a surface group. The quotient group is also a surface group. I believe it's not yet known whether this extension is hyperbolic. If it is hyperbolic, then one would be able to have an example where you have such an extension, but in the normal, when the subgroup is genuinely normal. Yeah? So which means that you really need this genuineness for, I mean, so there the normal subgroup acts trivially on the boundary. Yeah? So you want a genuine action of a totally disconnected group. Yes. Oh, the Hilbert-Smith conjecture. The Hilbert-Smith conjecture basically says that, look, if you have a compact TDLC, it cannot act faithfully on a manifold, topological manifold, which is all that we have here. I mean, there are various versions of this which are, so diffeomorphisms was, I think, already Montgomery-Zippin, maybe some others. Okay, so yeah, but that was the conjecture. Okay, conjecturally, yeah. So for instance, here's something that. So for instance, can the quotient be a hyperbolic building, Bourdon building? That's not a manifold, but you still expect that something happens. So what are the examples that are easy to construct? Just locally finite trees, Bassett trees. Those are relatively easy to construct. That's what I'm going to get to right now. Yes.
You should never have an example where the boundary is S4.
That's right. That's right. The boundary should not be the only possible manifold that it could be is a sphere. Yeah. And that would be ruled out by the Hilbert-Smith conjecture. All right, good. And now I think it's high time I actually gave some genuine examples because they're going on and on. Okay. Yeah. Yeah. That's probably true. Yeah. But the thing is, the quotient, it's a quotient space, right? So it's not that, you want to have a section. So what it should mean is that this extension does not have a QC surface group which maps faithfully down to the, yeah, that's what it would mean. Yeah. Okay, so what are examples? H is phi 1s, and so what's the construction? So you have, it's something like this. I'll say what this means here. So you take two copies of a surface group, and you have a characteristic subgroup which is a finite index in both. Okay, who are these due to? So this is due to Min. Yeah, so it's probably around 2010, thereabouts. So what are you really trying to do? You look at two, you take a particular surface group, you take a finite index subgroup of that, and let's just say you double H along that. Yeah? That's not going to be hyperbolic. Yeah? What you now do, and this is H1, so H is to H1 is finite. And what does this P mean? Twist by a pseudo-Anosov automorphism of H1. Yeah? So there's some further criteria. It's basically, it's in terms of the lamination. So H1 is now a surface, it's a finite index subgroup of this guy. And on one side, you have the identity inclusion. On the other side, instead of the identity, you twist by phi to the power some large number. And what do you have to ensure? So H1 is now going to give you some lamination. This is this is a hyperbolic plane basically as the universal cover. So H1 is now going to give rise to a lamination there. That's going to get translated by elements of capital H. What you want to ensure is that these different translates of the lamination are different, which means basically two leaves, they do not overlap along a ray. And that's the same thing as saying, by a limiting argument, it's basically saying that a lamination and its translates by these finitely many translates by the ambient H. If you take any leaf in one and any leaf in the other, and you project one to the other, that's bounded length. Okay, so that's this construction by Min, and H free, similar construction, but of course, free groups have a more convoluted theory because of, fully irreducible, essentially the same argument, but with a little bit of a twist, but this is due to Pritam Ghosh, again, from a few years back. So essentially the few candidates that were there, yes?
Impressed by how you deal with your name.
See, this is what you have when you get smart collaborators who decide to heckle you. Okay, all right. Okay, good. So, yeah, so basically the similar thing happens when you're finitely generated free, and it's essentially the same criterion in terms of laminations, because there is a theory of laminations due to Mosher and Handel. And even before Besvina, Fein, and Handel from 97, that's the fully reducible case, and that can be done. So yeah, so essentially, oh boy. Okay, so that's so basically it says that the few possibilities that were there in this theorem with Neer and Alex, that there are examples which, I mean, where this kind of thing genuinely happens. Okay, so so there are genuine examples. And oh yeah, so G is this. No, that's so before, without phi it is not. After twisting by phi, I mumbled something about sufficient conditions about the lamination, and so if you choose your phi appropriately, then for some sufficiently large power, this works. And it's also true that if you take some sufficiently large power, you're really going to get a free product with amalgamation. Okay, good. So that's about as much as I'll say about hyperbolic commensurations. And now, right, move to the case where I haven't yet defined what an elliptic commensuration is. Oh, it's the same thing. Just where did I do this? Yeah, H. H is free. H is finitely generated free. Same. G is also, you take a fully reducible hyperbolic automorphism of a free group, take the free product with amalgamation along a finite index subgroup, twist along the edge group by a large power of this fully reducible hyperbolic. Yeah. Yeah. No. If, no. No, it's a finite index, just a finite index subgroup. Yeah. If it's characteristic, you're in trouble, actually. Because you want the different translates to change things around, yeah. Yeah? The Schlichting completion in more explicit terms in this example. So basically what you're really, I mean, so the base guy is fine. It's the base guy is the Bassett tree. That's the graph. You're really asking for what's the H bar. Yeah? The finite, so it's going to be a completion of H with respect to some family of finite. Yeah, so the G bar is going to be exactly the finite index inclusions that you have of the edge group into the free group, into the vertex group. So this structure is going to replicate in the Schlichting completion of G with respect to H. So what you really want is what are the finite index subgroups of H that you're getting. So you really want what H bar is in this particular setup. And that has to, I haven't worked out any example, but this should not be too hard. I mean, it's essentially what will be basically is you look at the different finite index guys and you take loops here and what are the, what will be the collection of finite index subgroups that you get in the process, take the profinite with respect to that collection. That's the general, I've not said anything new, but it's, I mean, that will have to be actually worked out. Okay. It's going to be pretty far from being arithmetic, for instance. Okay. And I think this is a question that you had asked in a different context, and I'd said no. But now I'll define an elliptic commensuration, and the answer to your question will be yes. All right. So, definition, G, H, G is, again, this is non-standard, strongly elliptically commensurated if G is quasi-isometric to H with the base graph. And this is equivalent to saying, and I think this is something that has been worked out by Alex. This is saying that for all G, there exists a K such that for all G in G, phi G, which is the induced map. See, a commensuration certainly is it's some quasi-isometry of a group to itself. Yeah. Therefore, it has a natural map on the boundary. So that's what I'm calling phi G. This is from boundary H to boundary H. This guy is KQC. So all the maps are KQC, which is, I don't want to say something inside the group because, yeah, I mean, if it's a commensuration, there'll be big blobs that will be left empty. Yeah? I can't quite say it's a quasi-isometry inside. However, you can actually, I mean, it's easy enough to say this on the boundary, and then there is, you can put in, I mean, there's an alternate way of saying this where there is a, yes, Henry? Okay. Yeah. So, right. So there's another way of saying this. There's what you say is basically, look, there is some ambient hyperbolic space, yeah, such that inside which all these groups sit, and the whole group G acts by uniform quasi-isometries in the space. So that's basically taking this boundary and putting flesh inside. Yeah? It's from the boundary inside. Okay, good. And curiously, so yeah, so elliptic commensurations have been actually what, yeah. So I'll change a letter here. So elliptic commensurations really, I mean, yeah, they're a thing due to, this is with, so what is the statement? That you have lambda contained in L. This is a lattice, and this is, let's say simple Lie group. Is arithmetic if and only if the commensurator, but now you don't look at the abstract commensurator, you're really looking at all elliptic commensurations, which basically means that isometries of the ambient symmetric space, which is L, of lambda is dense in L. So, for instance, SL2Z is arithmetic. Yeah, please don't ask me what arithmetic is. Yes? Yeah, that's a definition. That's the best possible definition. Fantastic. Yeah. So anyway, so it's basically if you have SL2Z, it's actually one has to fiddle around a little bit. So you look at PSL2Z, projectivized SL2Z sitting inside projectivized SL2R. And then you look at the commensurator of that, that's projectivized SL2Q. Since Q is dense in R, everything. Okay? So that's that side. So from arithmeticity, so essentially it's basically integers in some number field, some Lie group over it. Then you look at the rationals there. Rationals are dense. So one side is rather easy. Yeah? The converse is really Margulis's theorem. Yeah? It's a topological, soft topological characterization of arithmeticity. Okay. And so for the rest of this talk, which is, you're giving me 2 minutes extra. No, 2 minutes extra, that means it's 3:52. Okay, very good. Good. All right. So for the rest of the talk, I'll just focus on this class of spaces, and I will and I'll try to ask, or address the question where lambda, so replace lambda, by gamma, where this guy is discrete, Zariski dense, and infinite covolume in L. L is again simple Lie group. So these are called pin groups by, this is the name that was given by Sarnak. Yeah, okay. All right, and so here's the question. Okay, let's just go. So let's call this has a name. So Greenberg in the 70s and Shalom in the early 2000s, they basically, so let's call this, I'll give this thing a name. This is a hypothesis. Basically says that the commensurator of such a thin group is discrete. Okay, so it's a hypothesis. And I won't say whether I believe in it or not. That's going to be a theological discussion. Let's not put it there. Okay, so yeah, but here's the thing. See, Margulis's thing for lattices, discrete means non-arithmeticity. It's a fairly strong assertion. Yeah? And so if you strengthen that hypothesis, you should get lots of consequences. Yeah? So here's the thing, and I'm going to say that if GSH holds, okay, and this is joint work with David Fisher, Thomas Koberda in various forms. Wouter. Oh no, this part is with Van Limbeek. Okay. If this Greenberg-Shalom, does that stand for something more? GSH does not stand for anything else, right? Okay, good. So if the Greenberg-Shalom hypothesis holds, then you have lots of marvelous consequences. Yeah. So first, this is a particular form of the Margulis. It's what's called the Margulis-Zimmer conjecture. I'll just state the particular case which is relevant here. So take SL2 Z1 by P. Gamma contained in this implies, so gamma is commensurated, that then gamma is finite index in the ambient or finite index in SL2Z. So this is a kind of a Margulis-Zimmer conjecture is a considerable strengthening of the normal subgroup theorem. Basically says that, look, if you have an S, I mean, these are guys are called S arithmetic lattices. So essentially what you do is you take some arithmetic lattice, so there's some ring of integers over which it is defined. You invert finitely many primes, then look at the new guy. I mean, so here you've taken Z, you've taken one prime and you've inverted it, and then you have SL2Z contained in this. So this guy is a lattice in SL2R cross SL2QP, and the only commensurated subgroups are things that are staring at you, the finite guys, the cofinite guys, and things which are of finite index when you throw away this prime. Yeah? That's it. Yeah? So that's the Margulis. So this is this particular case, and I mean, essentially, as soon as you have the S arithmetic, this number of primes that you're inverting, so long as it's non-zero, you get the general form from this Greenberg-Shalom. Yes, Nick. Gamma is thin. No. So gamma is just Zariski. No, I don't have any assumptions. So gamma is a subgroup which is commensurated. What are all subgroups? What are all commensurated subgroups of SL2Z1 by P? So this is, yeah, so you use this GSH to say that essentially thin guys cannot happen here. Thin guys cannot be there. Okay, so this is one such consequence. Second. Oh, yeah, oh, semi-simple. Yeah, this is someplace where I really need semi-simple. Okay. This is semi-simple where and p-adic. So Archimedean, non-Archimedean, all that stuff, yeah. All right, this is one consequence. And there are a bunch of others. So despite the grace that it's so the condition is really in SL2R cross SL2QP, where you require thinness. And so yeah. Okay, and so one other thing is you look at 1101 and 10Q1, where Q belongs to -4 intersect rationals. So this is not virtually free. This is, I mean, it's a 2x2 thing. It's an old one. Yes, just a moment. Linden, Ullman, and experimental evidence in favor of this. Okay, so in the last 2 minutes, and then there's a host of other consequences. So of course, I mean, it's to be expected. You strengthen hypothesis, you're going to get stronger conclusions. So is this at all known? So GSH holds for first, and this is where the name comes from, finitely generated subgroups of PSL2R. This is Greenberg. This is in the 70s. Second, finitely generated subgroups of PSL2C. And this is where, this is by Chris Leininger, Darren Long, Alan Reed. That's where I started off. And then, yeah, it's complete. This is around 2011. Third, if the, oh boy, let's, now I've used up all the letters. Calligraphic L gamma, bound in, let's say, G mod B. Okay. Boundary X is not all of mod B equal to X. So think X is a symmetric space, so the rank 1 symmetric space, it has a boundary. This guy is the limit set. So if the limit set is not full, then also this the Greenberg-Shalom hypothesis holds. So really, you're reduced to looking at examples where the limit set of this thin group is everything. Yeah? So for instance, gamma is genuinely normal in lambda. This is a lattice in a rank 1 group, rank 1 Lie group. And this is true, and I think the early results were with Thomas, and the final thing is with Fisher and Limbeek. Oh, and I should have said this is Nick Brody. Okay, so stop it. Thank you. Yeah. No, if it was known not to hold, then we wouldn't have called it a hypothesis. So the jury is out as to whether it's true or not, and I've given you some sample of consequences that you would have, and then of course, I mean, the thing is, okay, if you're getting so many things for free, if you just have one thing home, it's probably not true. Yeah. So for the general thing, I mean, what's the Greenberg-Shalom? Yes. So this is an SL2R. So this is an SL2R, 2 cross 2 matrices in SL. Yeah. So no. So for instance, I mean, here's the thing. The Greenberg-Shalom hypothesis is probably, most of the features are now localized in, say, discrete subgroups of SL2R, which have full limit set. But these are infinitely generated, right? So SL2R cross SL2Q. If Q is a prime, let's say it's, oh boy, this is 1 by, let's say 1 by P, 2 by P, yeah? Yeah. Yeah, so if it's let's say SL2Q.